Okay, so did you turn it on?
Just now, yeah.
Okay, here. Okay, so let's return to this hyperboloid, and I want to do that because I had a sign. I was confused about the signs last time. Okay, and the resolution of this is interesting. First of all, these are the points, and they're embedded in some. These are points in three-dimensional Euclidean space. Well, let me not say three copy, in other words, R3. So they're vectors of three real numbers. They satisfy this equation, which is the hyperboloid equation. But now here's what's weird. The basis vectors always are partial of the points with respect to the coordinates, so they're the same. They're these vectors. But now here's what's interesting. You see, the squared distance between points is ds squared, and so this is e theta dot e theta squared plus e phi dot e phi squared. But what these dot products are depend upon what metric we impose on this space R3. And there are two choices. We can first do something weird and say that this metric is going to be 1, 1, minus 1. That means that z is a time coordinate. And if we do that, then what is ds squared? Well, then e theta dot e theta is cos squared minus sin squared, that's 1. So this is r squared d theta squared. Or let me. So if this is the metric, then e theta dot e theta is equal to 1. E phi dot e phi is also equal to 1. And ds squared is equal to d theta squared plus d phi squared. Wait, I left out. The dot product of these two is, well, it depends upon the metric, of course. So the dot product of e phi with e phi is actually sinh squared, it's not 1. So it's sin squared of theta, and so this is sin squared of theta d phi squared. So that's what the distance between two nearby points is. This is a two-dimensional space, curved space, in R3, but R3 isn't Euclidean 3 space. It's a 3 space with 2 space and 1 time coordinates, effectively. And so this is the metric, and what happens? Well, what we can do is we can change variables in a sort of cute way. We can say that we have a dimensional scale factor A, and we set K equal to A over R squared, and we set R equal to R sinh theta divided by A. And then if you plug that into this, you see that, first of all, ADR is equal to R cos theta d theta. So d theta squared is basically dr squared over cos squared. And so this thing, this ds squared is a squared dr squared over cos squared of theta. And then sin squared, well, sin squared is just ar over r. And so this is plus a squared r squared d phi squared. I somehow lost an r there. Oh, there was an r squared. I left out an r squared here. And in fact, the d theta squared also has an r squared in it. So I'm screwing this up. But anyway, this is what one gets. And now cos squared, of course, of theta minus sin squared of theta is equal to 1. So this can be rewritten in terms of sin squared. And when you do that, what you get is a squared times dr squared over 1 plus kr squared plus r squared dp squared. Okay, so that's what the metric is. So let's start all over again. These are the points. They form a two-dimensional surface in 3 space. They form a hyperboloid. These are the basis vectors. The distance between two infinitesimal points with coordinates that differ by d theta and d phi is then this. But what these things are depends on the metric. If we choose this as the metric, then what we get is this. Okay. On the other hand, we could have chosen as a metric just 1, 1, 1. And then this hyperboloid is an ordinary hyperboloid. That is to say, this space that we're embedding it in, this 3 space, is ordinary 3 space. It's Euclidean 3 space. And then the thing looks like this, basically. X, Y, Z. And so Z squared minus X squared minus Y squared is R squared. It's the ordinary hyperboloid. And then when you go now, E theta dot E theta is different because it would be cos squared plus sin squared, not minus sin squared. And so E theta dot E theta is cos squared theta plus sin squared theta, and I left out an R squared. And E phi dot E phi, well, it's E phi dot E phi is the same because E phi doesn't have any C component. And so this is the same thing, sin squared theta, and I left out an R squared. Okay. Now we get a different formula, and one that's a little bit, it's less attractive. Looks like this. 1 plus 2k r squared dr squared over 1 plus kr squared plus r squared d phi squared. So this is what we get. Now, this, you may wonder, why am I going through it? It's just to fix a minus sign. This is actually, some of this is actually important. Actually, did you get this board? Okay. What's important here is that this case with this metric is maximally symmetric. And you can sort of see that this is a nicer formula than this one, which is kind of clunky. this is a nicer formula. There are only 3 maximally symmetric 2 surfaces in 3 space. One of them is this. The other one is one that I did last time without any trouble, because it was just it's just the how shall I say, the now I've lost track. Right, it's just the sphere S2, and let me remind you what that turned out to be. The sphere is the other maximally symmetric space, and so for it, the sphere, the 2-dimensional sphere, which is just the ordinary sphere, has with these same choices of coordinates, it's a squared dr squared over 1 minus kr squared plus a squared r squared dphi squared. So this and that are very similar, and in fact they are the only 2 non-trivial maximally symmetric 2 surfaces. The other one, of course, is the plane. There are actually 3. So there's the plane, the sphere, and then this funny hyperboloid. Now, here's what's really important. Suppose we jump up in dimension by 1. Then we basically have 3 maximally symmetric spaces. Ordinary Euclidean space, flat Euclidean space, and then we have something that looks very much like this, namely a sphere embedded in 4 space, and then something very much like this. And these form there are then 3 maximally symmetric 3 spaces, and one of them is just trivial, it's just Euclidean 3 space. And if you put them all together, they constitute the space part of the models that we use in cosmology. And in fact, the cosmological model is very simple. The time part is just dt squared, or minus c squared dt squared. So the reason why this makes sense is that as far as we know from observations, the 3 space we live in is maximally symmetric, and there are only 3 choices. On the other hand, frankly, I certainly don't understand time at all. I mean, I sort of float through it and find it very confusing. And so it could be that our description of cosmology with just time being t and just being the real line. So in other words, our cosmologies are the real line for time plus, and then one of 3 maximally symmetric 3 spaces for 3 space. That's the cosmology. Okay, I think since I've gone through this, I should quickly do. Let me show you again then what this. The sphere thing, of course, embedded in 4 space, is the points. We can write them this way as r, and then it's sine chi or chi, sine theta, cos phi, sine chi, sine theta, sine phi, sine chi, cosine theta, cosine chi. Okay, so those are the points. They satisfy r squared is x squared plus y squared plus z squared plus w squared. For, in other words, this being x, y, z, w. And you can compute the vectors. In other words, e chi is partial p, partial chi, E theta is partial P partial theta. E phi is partial P partial phi. I think I did these last time, and this, if we choose as the metric 1, 1, 1, 1, then we get just the ordinary three-sphere, and instead of going through all that algebra, let me just say it's E chi dot E chi squared plus E theta dot E theta squared plus E phi dot E phi squared. And if you go through the algebra and make those same AR is big R, sinh chi actually, what you wind up with here is A squared dr squared over 1 minus kr squared plus r squared d theta squared plus r squared sine squared theta d phi squared. Okay, so this is the spatial part of one of the Robertson-Walker cosmologies, and the whole thing. So let us put an S under that for spatial. The whole ds squared is minus c squared dt squared plus ds squared sub s. Okay. So the Robertson-Walker line element or distance between points then is of this form. So it's a maximally symmetric three-space together with a simple time. And the other case is the hyperboloid H3. And I'm sort of repeating myself a little bit here, and I'm sorry about that. This is R sinh chi. Let's see, are those actually the same coordinates? Right, it's actually just, oh, wait a minute, let me make sure I've got this right. That is, I see. All right, so no, this is not the same. Sinh chi, sine theta, cosine, all right, here. Sine theta, cosine phi, sinh chi, sorry. Yeah, sinh chi, sine theta, sine phi, sinh chi, cos theta, sinh chi. No, cos. See, I've got all these equations, and if I'm on the wrong line, I copy the wrong thing. So these are the points for the hyperboloid, and now you define your basis vectors in the same way: partial chi, e theta is partial p partial theta, e phi is partial p partial phi, and now we're going to use, if we used the same metric, we wouldn't get a maximally symmetric space. Because now we use the metric m is 1, 1, 1 minus 1, making this w here a time coordinate. By the way, these points satisfy r squared is actually, it's minus x squared minus y squared minus z squared plus w squared. Right, okay. So there's actually a minus sign here that I need to fix. Okay, if we now go through all the arithmetic, what we get is ds squared with this metric, these points satisfy, which lie on that hyperboloid. We get a squared dr squared over 1 plus kr squared plus r squared d theta squared plus r squared sine squared theta d phi squared. Okay, so, and this is the other Robinson-Walker spatial metric, and the full Robinson-Walker metric is minus c squared dt squared plus ds squared spatial. Okay, so let me put it to you again. There are three maximally symmetric three spaces. The other one, of course, is Euclidean space, and then the s squared is just minus c squared dt squared plus, you can write this down, but it's effectively a squared dr squared plus r squared d theta squared plus r squared sine squared theta d phi squared. So this is just Euclidean space with a stretching factor A. So, so those are our models of cosmology, and they're related to this idea of maximally symmetric spaces. And the amazing thing is that there are so few of them. So let's see, what should I say a little bit about maximally symmetric spaces? It has to do with the metric. So we know that g prime of x prime. You okay?
Yeah, no, I'm fine. Just
we know that g prime of x prime is g, say, or JL of x, and now, God, I forget which way this goes, because I got it wrong the other time. All right, so let me just flip back to earlier. Okay, so this is partial x, partial x, partial x prime, partial x prime. Now I need to get the indices right. This is I, and this is K, and this is J, and that's L. So there's a prime, and that's a J.
So, J or I?
On the bottom?
So you have to-
Oh,
you
you're
have
right,
to-
damn it. Yes. Right. These guys match those guys, and then we have these guys match those guys. Okay, so this is the way the metric transforms. It's a second-rank covariant tensor. But what is the criterion for maximal symmetry? Well, maximal symmetry means that we can remove this prime. That is to say that this is equal to g of gik of x prime. So in other words, anyway, this is the criterion for maximally symmetric spaces. And one can pursue this and then show that for two spaces, for three spaces, for spaces in two-dimensional spaces in 3 dimensions, there are three of them, and for three-dimensional surfaces in floor space, there are also 3 of them. And these are the ones that we use for cosmology. Okay, so let's see. So let me.
I have a question.
Yeah.
This last part you wrote is, what does the subscript give?
That should be IK, right?
Okay, so it's just the same as the left-hand side?
Yeah.
Without the
it's-
prime?
That's right.
So should the x have a prime one or not?
Excuse me?
This x here, is it GIK of x prime or just GIK of x?
No, it's GIK of x prime. We just removed one prime. Of course, I'm doing this from memory, and I should have written this down, but I didn't. In any event, the words associated with this, or the people who studied this, one was a guy named Killing, gruesome name. Anyway, he analyzed this and found that there were certain vectors that played a role, and these are called Killing vectors. It turns out that Sophus Lee was also involved in some way, and that Killing also discovered a lot about Lie groups, and there was some bad feelings between Lee and Killing because they both have a claim to discovering Lie groups or Killing groups. Anyway, Lee has a much nicer name, so I'm happy that the name Lie groups was what's so wrong. Okay, so let's see.
And I have other questions, can I ask?
Yeah.
So your points, and I missed Thursday's class, so if you covered this in Thursday's class, then I should know it and just let me know. Your points have chi, theta, phi, and there are 4 coordinates, so this is a 4 space.
Right, the idea is that this is a 3-surface embedded in 4 space.
Okay. And how is W related to T?
Oh, it's not that it's related to T. It's that, well, in this case, we're just imposing this metric. So this is the surface of a 3-sphere in 4 space, so there's no T at all. This is just S3.
Okay. So the reason I was asking is because I was wondering.
Yeah,
if
I owe you at least one candy. How many do I owe you? Did anybody else ask a question?
The reason I was asking is I was wondering how you were getting the negative with all positives in the metric, but I guess that has to do with the W instead of the T. The negative for your.
All right. You want me to?
I can give it out.
Okay. Trust me, you said. Or I said. You know. Okay, so the bottom line here is that this modern view of cosmology is really, really very, very simple, essentially. It's that space is maximally symmetric. You have 3 choices, and they differ just by whether this K is positive, well, in this case, it's positive with a minus sign. In this case, we imagine we have a minus sign and K is negative, so we get a plus sign. Because I was thinking of K as positive. Anyway, so that's another minus sign that's creeping around. I think maybe this is a good time to do a demo. This is maybe my favorite demo because it's the easiest one to do. And it's in fact a demo that was made by, I think it was an engineer in Princeton, possibly at the Institute for Advanced Study or maybe just at the university. Anyway, this man was a friend of Einstein's, and for either his last birthday or his next to the last birthday, he made him something very much like this and called it a demo for the principle of equivalence. And So, and Einstein was delighted by it. And so, do you want to do the demo?
Sure.
I did this in another class, so
This is a little higher, I think.
go as high as you want.
You don't have to make it higher than you can reach comfortably.
Okay, so let's, well done. All right, so here's what happens. You see, if the thing is sitting there, there's a spring in here. It's not strong enough to pull the ball up because the ball has a certain weight in our gravitational field. On the other hand, when you drop the thing, in the free fall coordinates, there's no gravity. And because there's no gravity, the string is strong enough to pull it around. Now, I see you doubting this. Why don't you come up and do the demo? Well done. It's like, let me do a movie. I almost never do movies, so I don't know. I guess movies are called videos now. All right, so do it again. So go on up to the top. Okay. Now, did I make a movie or did I screw up? Oh God, let's see what we got.
Oh, you got it.
No, I think I didn't.
Oh, you got 5 seconds of it.
Oh, Christ.
Oh, wait.
All right, I screwed up. I've got a marvelous video of the floor. How do I get rid of the damn thing? Yeah, that's it. Delete video. Okay. Boom. All right. You want to do it one more time? Wait a minute. All right. Okay. Now what do I do? I press video.
Just press it once to start it. Just
Okay. Drop
press
it. Do it. Marvelous. All right. Let's see if we've got it.
Yep, we're good.
Good. Thank you.
Yay.
All right. Now you.
We're true scientists. Yeah. Do it yourself.
You want me to make a movie? Are you doing it?
No, that's it. Are you sure?
Alright.
Awesome. We're gonna movie.
I'm gonna post this in the group chat.
Oh no! We broke physics.
Oh God, physics is broken. Now I don't even know how to delete the damn thing.
Get rid of the evidence.
We're going to erase that one. All right, wait, I have to get it set up again. Wait, let me get back to it.
Okay.
Okay, do it.
There we go.
Bravo. Okay. Bobby, you want to do it? Oh, come on. Oh, you did it? Done it in the past?
Yeah, I didn't understand it, but I didn't understand it at that time. Yeah, we did it for the last few years ago.
All right. Okay, so this is the demo. I learned about this reading Z's book, Einstein Gravity in a Nutshell. It's quite a good book, but the title is kind of misleading because his nutshell is about 1,000 pages long.
He had a big noggin.
Hmm?
He had a big noggin. Old Einstein.
All right, say it again.
I said he had a big noggin. His nutshell was a little bit bigger than the rest of ours.
Okay. All right, so let's see where we were. Let me just mention something completely trivial, which I can maybe do on this little bit of board here. Okay, so there are various notations for derivatives. One is f sub x, and then you can write it as partial sub x sub f, or you can write it as partial f, partial x. Okay. Then, on the other hand, what we've got is we call our coordinates x1, x2, x3, and x0, I guess. So a good notation is f comma I, or partial sub I of f, and that means partial f, partial xi. And one can then, here, let's go. Maybe you should share the thing, since you're sitting on opposite sides of the camera. One of you can move it when you're in one position, the other one you're in the other position. This is a very economical notation because f sub comma ik is partial to f, partial xk, partial xi. So it's a double partial derivative. And that's a nice notation. Now, we were talking about these basis vectors. The basis vectors are the derivatives of the points with respect to. She can do it when I'm in the back of the room.
She's really focused.
Ivy can do it when I'm in the front of the room. What's your name again?
Oh,
Say
Cayman.
Cayman? Cayman can do it. All right, so those are the basis vectors, and these vectors AK, EK, which are GK, L, say, E sub L, these are orthogonal or dual. And these form a nice projection operator, really. In other words, if we have EK and then an EK here, and we sum over K, and we act on that on something, let's say, Fi EI, and I'm dotting this through, and this vector is just sitting there. And of course, this is a sum, we have sum of k and I, E sub k, delta k I, Fi, and then this becomes some ek, fk. So this thing is like an identity operator. It's an identity operator not in the full space, the embedding space, but in what's called the tangent space spanned by these things. These are called tangent vectors. And what might be nice is to write these as, a sort of tangent identity is then like, if we use the Dirac notation, it would be like this. Namely, that this guy is dotting into the vector that follows it, and this vector is just sitting there forward. Now let's see. You people weren't in 466, so let me explain this Dirac notation here. And let's just explain it in the simple case of just ordinary Euclidean space. Let's suppose E1, well, of course, if we're in a Euclidean space, then these raising and lowering indices doesn't make any difference. So let's just say E1 is 1, 0, and E2 is 0, 1. Then if you have E1, E1, this is 1, 0, 0, 1. So this thing is like the transpose. But it sits to the right here, and the idea is you multiply them together, really. And so what you get here is 0, 1, 0, 0. Yeah.
So do you have E1, E2?
This is a 1.
Right, so then if that's true, then your row should be a
You're
1.
absolutely right. I screwed up. Let me get a candy and my
I don't need any
eraser.
candy. I don't need any candy. Yeah, Tom.
All right, so who else wants candy?
Yeah, Tom.
Ivy, you need a candy?
Sure.
In fact, everybody who did a demo gets a candy.
Oh,
Oh, good.
no.
Good job, Fraser.
Yay.
All right, so
Missing out, man.
thank you. Okay, so this is 1, 0, 0, 0. E1, E2 then would be 1, 0, 0, 1, and this is 0, 1, 0, 0. E2 cross E2 would be 0, 1, 0, 1, and that would be 0, 0, 0, 1, and then finally, so let's see, is that E2, E2? Okay, E2, E1 is 0, 1, 1, 0, and so this is 0, 0, 1, 0. And so you see that if you have E2, E2 plus E1, E1, this is then 1, 0, 0, 1, because you add this one plus that one. And that's the identity operator, or the identity matrix. Now, in general, if these are tangent spaces of some sort of a space or surface in a higher flat space, then this thing is an identity operator in the tangent space, or equivalently, it's something that projects an arbitrary vector down into the tangent space. The space of vectors that are tangent to the surface. Okay, so let's see. So we've got I love it the way you can just throw that thing against the screen and it sticks. All right, so this is an idea of covariant derivatives, and I think maybe I'm going to do it a little differently from the way I did it last time. So let's start out with something that's a nice scalar. So these are the basis vectors, and these are some contravariant coefficients. And now, let's act on it with a projection operator and then take the derivative of f with respect to xl. Well, what we have here then is, and this ek is dotting into that. And so now we take the derivative of f, and this is partial fi partial xl times ei plus fi partial ei partial xl. And so now this gives us ek, and this is the dual vector of e lowercase, so this is orthogonal, and so this just gives us partial fk partial xl. And then this one gives us something new. The ek is just sitting there. And so what we have is fi ek dot partial ei partial xl. And this thing is in standard notation of relativity. This is partial fk partial xl plus fi gamma k, and then let me make sure I have it right, il, yes. This is called a Levi-Civitak affine connection. It's also called a Christoffel symbol of the second kind. But what you see is that it's really what happens if you differentiate something with respect to the coordinates, and then you hit that derivative with a projection operator that keeps things in the tangent space. So this is still on the tangent space, and of course we're summing over k. And there are various notations for this. We can call this ek fk semicolon L. That's a notation for covariant derivative. Instead of comma, semicolon. Another way of thinking of it is as ek d d sub L of f, and I think we really need a k somewhere, so I'm going to just put it there. In any event, that's what one has. Another notation is a triangle notation. ek triangle L fk. These are all equivalent notations. Now, what is clear here, you see, is that gamma k il is ek dot partial ei partial xl. That's just from the definition that this thing here is that. But on the other hand, this ei is a basis vector, so this is ek dot partial of the point with respect to xi, and then partial xl. But derivatives, partial derivatives can go in either. They commute. You can turn the thing around. This is the same thing as ek dot. Whoop, this is partial 2. Partial 2 p partial xi partial xl. And now this is ek dot partial el with respect to xi, and then this is gamma k. If that was il, then this is li. So what we see is that this Christoffel symbol is symmetric in the two lower indices. There's a more general formulation due to Cartan in which instead of having the e's as the basis vectors, there are other vectors that aren't basis vectors, but are simply vectors that allow you to write the space-time metric in terms of them and in terms of the eta. I think I'm going to skip over that. If you want to read the notes, it's there. An important thing about these covariant derivatives is that they're not. I'm sorry. About the affine connections is that they're not tensors. That is to say that this thing here, gamma k li, which is this, or gamma k il, which is that, is not a tensor. And when it transforms, what you get is you get an inhomogeneous piece. And the reason is that tensors transform homogeneously. This thing transforms in such a way that let us put it this way, gamma prime k il is what you'd expect. So what you'd expect plus an extra term, and the extra term is partial x prime k partial xn partial 2xn partial x prime l partial x prime I. So this extra term means that the gammas are not tensors. All right, you can skip on there. All right, let me say something about parallel transport now. And one reason to say something about it is that this is I can do sort of an example that's visually clear. Okay, so I'm going to stop seeing. So let's look at okay, so that's meant to be part of the surface of a sphere. And so this is phi equals 0, this line. This is phi equal to pi over 2. This is theta equals 0. This is theta equal to pi over 2. Okay. Now, here's the cool thing. Suppose you start with a vector that's actually E phi. And you parallel transport it. That means that you transport it in such a way that you keep its dot products with the basis vectors or tangent vectors the same. Anyway, if you do that, what happens? It looks like this. So just before you get to the North Pole, this E phi is still E phi, but it's almost the same as E theta. And we can now say that it's turned into E theta. So now, if we move E theta down from the North Pole to the equator, and keep its dot product with the tangent vectors the same, well, obviously E theta just stays E theta. So then when it gets down here, it's just pointing that way. Now, if we pull it around back to phi equals 0, so maybe I should have put in a few arrows here. It just goes around this way. And so when we get back to the origin, it's pointing directly down. It's still, it's E theta, but it started out as E phi, and they differ by 90 degrees. And so there's a lesson there, namely, if you parallel transport on a flat surface, you get back to what you started with. If you parallel transport on a curved surface, you get something else. And in this case, it's off by 90 degrees. Now, when I was talking there about covariant derivatives, I was talking about the covariant derivatives of a scalar that I was writing this way. We can also talk about a scalar that we write, say, this way. In other words, that has covariant functions that are covariant times dual vectors. And now, what we would do is we would take I think maybe I'll do this. Instead of following my notes, I'll just wing it. How's that? All right. Okay, so now what we're doing is we're going to take, say, partial xi of v. Well, I better write v as VL EL. And then I want to hit this with, not with the thing that we previously had, which was E upper K, but instead E lower K, E upper K. So this is still, this projects dual vectors onto dual vectors. This preserves the dual space. And what will this be? Well, this will be EK partial VL partial XI E upper L, and of course this thing just gives you delta LK. And then the other term is EK dot partial EL partial XI times V sub L. Okay, so now we've got a new symbol here. What is this thing which is E lower k dot partial EL partial XI? Well, what we know is that this plus partial EK partial XI dot E sub L, that has to be 0 because that is just partial XI of EK dot EL, and that's just a Kronecker delta that's independent of coordinates. All right, this thing is gamma L, and I never know whether it's Ki or Ik, but of course it doesn't matter. So let me put it Ki or Ik. And so what this is telling us, since this is sum of these two is 0, is that Ek dot partial EL partial XI is minus that. And so this thing is then Ek, the Kronecker delta here and the sum over L gives us partial Vk partial Xi, And then this thing gives us minus gamma LKI VL. Okay. So it's the same rule, basically, as for the ordinary covariant, for the covariant derivative written in terms of contravariant components and covariant basis vectors. The difference is that this thing has a minus sign, and also that since the components are covariant, the Christoffel symbol comes in with an upper symbol here, an upper index here. So, and let me write down what the notation, maybe a little bit of notation here. So in other words, what we say here is V I semicolon L is VI comma L, ordinary derivative, minus VK Lord, good, it's IL, okay, I can VK, gamma K IL. Okay, so the difference is essentially this. Let me flip back to what the ordinary covariant derivative is, although it's actually just on the previous page, if I'm not mistaken. Yes. In other words, what we had here was Fk semicolon L is Fk comma L plus Fi gamma K I L. Now, to make things a little more symmetrical, since I've got IL here, I think I'm going to interchange K and I. If I interchange K and I, these guys become Ks, and these become Is. So this is a little bit better at comparing the two. And so in both cases, the first term is you just differentiate with respect to whatever the coordinate is, you differentiate the function. And then if it's covariant, you have a minus sign. You're then summing over a K here. But because the K here is lower, the K over here is upper. And because the K here is upper, the K there is lower. And then over here, the I just comes across as over here, the I just comes across. So, are there any questions? All right. So you may wonder why have two of these? Well, there's a curious simplification that occurs, namely that if you write this the other way, VL semicolon I, then this is VL comma I, but then this is VK. I've interchanged IL, but that doesn't matter, and then there's a K, right? So now the difference between these two, the complicated terms cancel. And what that tells you then is that VI semicolon L minus VL semicolon I is the same thing as VI comma L minus VL comma I. So in other words, the covariant curl is the ordinary curl. Sorry. Maybe I should write that down. Covariant curl is ordinary Cahill. So what happens if you have a tensor? Well, if you have a tensor, you just use the same rules. You just generalize these rules to the tensor case. Maybe I should just give an example. So let's. How much space do I have on the back side? Well, I have a little more space. All right, so let me just give an example of what happens. Suppose we have a tensor T IL, and we take the covariant derivative in the k direction. Then this is TIL comma k plus TJL gamma IJK plus TIM gamma L MK. Let me make sure I've got that right. Yeah, I think so. Okay, so that's how it works. And if it's if this thing is a covariant tensor, then you get some minus signs. There's something special that happens when the tensor's anti-symmetric. That's worth knowing. So let me just mention what it is. Namely, if you have an anti-symmetric tensor and you do AIL comma K plus A KI did I say comma? I meant semicolon. So the kth covariant derivative of AIL plus the lth covariant derivative of AKI plus the ith covariant derivative of ALK. What this turns out to be is the same thing with ordinary derivatives if A is anti-symmetric. So in other words, it is AIL comma K plus A KI comma L plus A LK comma I. So that's one of the symmetries, one of the remarkable simplifications. Now, let me just skip to the answer. This may come as a surprise, but it turns out to be true, and if you really want me to, I'll go through all the arithmetic. I'm going to have to erase something. All right, so this is important, and it just follows from what we've done so far, but there's a certain amount of arithmetic. It's in the online notes. And it's the following, that these things that we've been talking about that occur in the covariant derivatives, these Christoffel symbols, there's actually a formula for them in terms of the G's. And it's GSK, GKI comma L plus GLK comma I minus GIL comma K. So in other words, the metric determines these Christoffel symbols. And you sort of imagine that that's the case. Once you know that, you can derive the following result. That if you take the covariant derivative of the metric, you get 0. And the same thing is true if you take the inverse metric and take its covariant derivative, you get 0. So the covariant derivative of the metric vanishes. So these are all sort of juicy things that occur. May not seem juicy, but they're simplifications that are godsends to people who labor in the venues of general relativity. Let me say a word now about this business of embedding spaces. I think it makes everything much clearer. If you don't use embedding spaces, then what you have to do is you have to really think, you have to define everything intrinsically on the curved space-time itself. And one can do that, and most books on general relativity, especially hardcore books, do it that way. On the other hand, there are theorems, one of them is due to a man named Whitney, that you can always embed any of these suitably smooth manifolds in a higher dimensional flat space with a suitable metric. And by metric I meant this thing, this internal metric, or the metric of the embedding space. And so you can always do it this way. Once you do it that way, everything, it seems to me, is just intrinsically clearer and simpler. There's also a physical reason why this may be true. In string theory, one version of string theory is that we're living on a 4-dimensional brane in a higher dimensional space, and we're sort of stuck on the brane. And that's very much like saying that our 4-dimensional space is embedded in a higher dimensional flat space. And in that case, of course, if the string theory viewpoint is correct, at least with these branes and so forth, then it's more correct to take the embedding point of view. Let me say one more thing. I was talking about maximally symmetric spaces. And I was talking about maximally spaces first, 2-dimensional spaces, and we had these two hyperboloid. We had the hyperboloid that's maximally symmetric, and the other one that was kind of crooked. And then we had the sphere, which is maximally symmetric. And then we had the two 3-dimensional maximally symmetric spaces, as well as the trivial one, which is just Euclidean 3 space. Now we can say, what about 4-dimensional maximally symmetric spaces? Well, there are again 3 of these. One is just ordinary Minkowski space, perfectly flat. Dx squared plus dy squared plus dz squared minus c squared dt squared. Then there are 2 others. The 2 others are called de Sitter space and anti-de Sitter space. And here's what's interesting about these. Namely that, let's look at our cosmology now. What do we understand? The universe is something like, I should have looked at my notes more carefully, but it's 2/3 or 3/4 dark energy is the energy density. And then there's matter. Most of the matter is dark matter, and then there's some bright matter, which is us, and the lights and so forth. Now, if we go, we're now 14 billion years or so after the Big Bang. If we project another 100 billion years into the future, the universe will have expanded so much that the energy density of the universe then will be 99.99% dark energy, virtually no matter as fraction of the energy density. It'll be like the science budget fraction of the total federal budget. Everything will be the military budget, dark energy, that's a good term for that. Anyway, though there are some very good people who work in the defense sector, let me say that. I know 2 of them, 3 of them actually, 4 of them. Anyway, one of them's my son. I'm rambling on a tangent. The point is, if we go off into the future, it's all dark energy, and so we might as well neglect the mass part. Okay, now let's rewind the movie backwards. What does it turn into? It's just de Sitter or anti-de Sitter. So in other words, it could be that the dark energy isn't really dark energy, but really is just that we live in a maximally symmetric space-time apart from a little bit of matter that's sprinkled around time 0 or near time 0. Sprinkled time, I'm taking time 0 as being 0 plus or minus 14 billion years. Okay, all right, that's enough, I think. We can turn this off, unless there's a question.